We have successfully survived exam number 1. Hey, you guys can get on there. You can check out the statistics, in your own recitation section, your lab, your lecture section overall. Key stats I remember off the top of my head was that the overall median of whatever 300 some people was about a 79. So basically, almost half the population got an A or a B. This is good. Happy with that performance. High grade was 100. Nobody can say the exam was not doable. High grade was 100. We had an awful lot of high 90s grades. I'm guessing -1s, maybe some units, maybe some sign errors, maybe some calculator punch. A lot of high 90s grades. And low grade, I think, was a 19, which is actually higher. Out of 308 people, I could have figured we'd have some single digits. So low grade 19, I'm not that unhappy with that. And so let me give you a recap on what this exam means for your grade. The exam is 20% of the final course grade. So the way you can kind of normalize this is if you got a 50% on the exam, okay, then the median was a 79, so you did way worse than most of the people. That's true. Okay, if you got a 50, it means it costs you a letter grade. We typically use standard university scale in here, occasionally tweaks on borderline grades, but it's pretty standard, right? So if you got a 50%, it's one letter grade. Doesn't mean you're going to fail the course. Okay, now, students that get repeated grades of 50%, right, between this and the next midterm and the final and the MATLAB final, that's when you're not getting the C or better that's required to move on, in your program here. Okay, and so the thing is, make an assessment of your performance on this exam and try and come to an understanding of the reason for your performance. Okay, whether that is good performance or poor performance or average. No matter where you sit, make an assessment. Okay, because if you did really well on this exam, could be you're a student that had a whole bunch of this stuff prior, didn't put a lot of effort into it, you had no problem with the lines, quadratics, trigonometry, even the vectors, good physics class. Maybe you basically had to learn one new topic, which was complex numbers. Okay, and you executed well. Great. But moving on to exam 2, there might be 4 new topics that you really got to become proficient with to be successful. And then moving on to exam 3, the final, when we're doing integrals, differential equations, there might be nothing you've ever seen before in the content. Okay, so make the adjustment accordingly. Anybody that did well on the exam understands the kind of preparation they need to have, et cetera. But then do a calibration. Was a lot of this stuff you already knew? Or did you really prepare well and hard enough and then adjust accordingly? Okay, we usually get some resets of high grades on exam 1. Students kind of don't prepare a lot then for exam 2 and bam, low 80s or something when they were just coming off a high 90s. Okay, so I don't want to see that happen. The other one is if you had a really poor grade, if you were at the 50%, make a decision. Is the 50% or lower grade a grade you got because you're really struggling to understand this course material, and you feel like there's no hope for you? Nobody should feel like that in here, right? And so if that's the way you feel, step back and look at the resources we provide in this course, okay, and the amount of hours the TAs have and the instructors to see you and everybody else, and decide like, hey, if I turn things around, can I get back caught up where I need to be? Okay, if your grade is 50% or lower, and it's just a sanity check, like, hey, you're new to college, you really didn't study a whole lot, and now you realize you need to do more work, then that's great. Make an adjustment now. Okay. If your grade is 50% or less because you realized it would have taken a certain amount of work in order to be proficient and you didn't want to do it, and you still don't want to do that for exam 2 or exam 3, that's when you need to be thinking about, well, my grade is headed for a bad grade. Okay, so you've got to make an assessment where you are. Okay, but even a 0 on this exam that nobody got, okay, low grade was 19. Right, the grade of 19, they lost 80% of that grade, so they've lost, they're down to an 84% if they get everything else right, okay? And, that's a B, right? So is a person that gets a 19 likely to get everything else right? Probably not, okay? Could they get out of here with a B or C still? Yeah, it's possible, okay? But the ball's in your court if you're the 19, decide what you want to do about it. What's the reason why you were there? What can I do to turn that around? Okay, if you have any questions about your future in the class as we move forward, be cognizant of the drop date, right? Drop date is on the schedule, okay? And it is 25th? Friday the 25th is to drop in person. I think you can do online all the way till Sunday the 27th. Okay, so you've got some time in October to sort this out. Do not drop a class of any type without talking to the instructor directly. Okay, talk about your situation. Does it make sense for you? Again, this class, my position is any student that wants to work hard enough to be successful, any student can be successful with the grade of C or higher in this class. Okay, so really it's a decision about what's my current life situation. Am I working too many hours? Am I not able to put effort into this? Whatever it is, and we can talk those things through and decide what makes sense for you moving forward. Okay, but really, no matter how you did, you know, the big lesson in college exams is you got to put this exam behind you, whether you did well or not well, and now your focus is the next exam. All right, so do what you need to do on the next few sets of homework, get it all done, do your work, and then you've been through this once before. The process for exam 2 is exactly the same. The content will be different, right? And so as we complete the content in class here, we will post 3 old prior exams for exam 2, and that's it, same deal. All right, so if what you've been doing worked for you on this exam, then keep doing it, okay? And if what you've been doing didn't work for you, make some changes. If you're not sure what the changes should be, talk to me directly about what the changes should be, and I'd be happy to help you with that. Okay. Question?
So that the person with a 19, the highest overall grade they can get is an 84?
I don't know. Did I do the math right? So they lost 80% of 20% of the grade. Okay. So they lost 16% of their course grade. So they can get an 84 if everything else they did up until that point was 100. Okay. Now one thing I'm going to do is if I get a chance, it's actually important. I've got to do this. I like to put up a graphic I call why effort matters. Okay? So what I can do is I can assemble the spreadsheet when all the grades are updated in Pilot. Okay? And I can assemble the spreadsheet and just split the window in a spreadsheet in 2 regions. Grades above 90 and grades below 50. Okay? And if I put in the other window the homework grades, what you're going to see is the grades above 90 is going to be 2s, 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 2s across the board, all the homework all the time. The grades below 50, it'll look like a shotgun blast hit the homework spreadsheet. Okay? And it's just, this is why effort matters. Okay? And so part of what we're doing with this class, the content is really critical for your success. We've decoupled the prerequisite structure. We're saying this is what's going to enable you to move through 2 years of engineering. This is the really important stuff to motivate you for calculus, to prepare you for success in physics, statics, dynamics, circuits, all of that good stuff. Hey, but at the same time, the reason why we have mandatory attendance and written homework every week, and MATLAB homework every week, and lab every week, is we've got to condition your work ethic. It's like being an athlete or anything else. You want to be a high academic achiever, you just got to develop good habits, you got to turn stuff in, you got to do the work. Students that perform poorly, almost universally, don't do all the required work. Sometimes it's an ethic issue. Other times it's just like, hey, I'm paying for school myself, I'm working 40 hours, I don't have time. And then that's a real issue. You need to talk to academic advisor, talk to me about what's the best option to preserve your grades. Okay? But the bottom line is whatever your reason is. The structure here is about helping you develop the habits to be successful. And you can see the evidence in the grades every time, every term. Okay? Questions about the exam? All right, so if you look at the exam, the solutions are posted. If you're not understanding why you lost points for this or that or whatever, download the solutions as step 1. So you can file alone your own work, take a look at the solutions and say, oh, well, yeah, I totally missed the boat there, so I see why they took off the points. If you go through that process and you're like, well, they mustn't have understood what I did, or there's a problem here, then what you can do is talk directly to your instructor, so in that case, me. And the way we do this is, you'll notice different writing on the grading for all the problems, right? So 308 exams that we turned around by yesterday, Monday, for the other class, right? So we turned around in 5 days, 308 exams with partial credit, right? Every one graded by hand. And we did that by enlisting a gigantic team of graders. So we had 10 of our TAs serve as graders and instructors, okay, serve as graders. And the way it worked is we have buddies, 2 people, right? The same 2 people graded all 300 number 3s, and 2 different people graded all 300 number 1s, right? So to get consistency in grading, they sit down together with the answer key, grade a whole stack of these, make sure everybody's good on what the partial credit is, and then they can finish out on their own, but we get consistency in partial credit. Okay, so whenever exams are graded with partial credit, there's room for judgment call, and the key thing for them is consistency. So if you're looking at problem 2, and you're like, well, I made this error in problem 2 and it was a minus 2. And I made a similar magnitude error in problem 3 and it was a minus 4. As long as they did minus 4 on all the problem 3s for the same type of error, that's still consistent, right? So you're not going to see necessarily consistency across problems, right? But any 2 students with the same mistake on the same exam problem should basically lose the same amount of points, okay? And the TAs have bent over backwards to try and make sure that happened. If you feel like it didn't happen, if you have clear evidence that the person sitting next to you got minus 2 and you got minus 4 for the same mistake, bring that to our attention and we will rectify it. Okay, but we do a pretty good job usually. The other one to check for, double check the tally. You know, one student did all the tallies and entering of all the grades. So you go through 300 blue books and add them all up and tally them and enter them. There could be a math error. So we've seen it time and time again. Somebody missed to carry in the 1, right? And all of a sudden you lost a letter grade. So, I mean, make sure you double check your tally, double check that your grade is what it really is. If you have issues with that, give me your exam. It'll go back to the original grader to make the decision on the correction. Okay, I'm not going to overrule grading decisions of the TAs that did it. Okay, questions? All right, so round of applause in my own mind, if not from you, on the TA's turnaround on this. I was really impressed. The largest scale enrollment we've ever had in this course. Turned this around in 5 days. We did not have issues. You know, we did not have issues. I think we had one case of students that during the exam had to be kind of moved around because it was kind of obvious, like leaning over, looking at the paper kind of activity, like almost to the point of you're definitely cheating, give me the exam, I'm tearing it up, like this close. Okay, those students were moved. As far as I can tell, that's the only occurrence that we had of that. Okay, we scrutinized the exams at makeup. They were carefully proctored. No evidence that we had any funny business there. So I was happy with the seriousness that you guys took, the academic integrity. It's really important. You know, don't cheat on a college exam of any type, this class or anywhere else. It is your academic future at stake. Okay. Is that enough about the exam? We're going to do some calculus, okay? So we're moving on. For my own entertainment again, attendance sheet going around. Raise your hand if you've had some calculus before, any point in your life. Big chunk of the class. Okay, now, so I can get a sanity check. Raise your hand if you haven't had any calculus before. The rest of them, not as many. There's more than that because that wasn't all the hands. Okay, so we've got a decent mix in here, and that's fine. So I want you to keep in mind, if you haven't had calculus, this material was conceived and written for people that never had any math past trigonometry. Okay, I want you to understand that. At the same time, if you've had calculus, this material was conceived and written for first-year engineering students, and we knew there's students going to be sitting in the classroom, particularly in the fall term, that have had a whole year of calculus, some 2 years of calculus. Okay? And so what we hope to achieve is really a better understanding of the big picture of what derivatives are, when we get there, what integrals are, and then very, very quickly, no matter how much calculus you've had, you're going to be working all kinds of problems using calculus that you never worked in high school calculus, that you're going to see why this stuff really matters in this building in our classes. Okay? And so we'll move forward with that. Okay, but to start out, today we're going to talk about derivatives, okay, and what is a derivative in engineering. And we do have a handout that I'll get to shortly that we'll pull up, but I'm going to go ahead with the numbers, take one and pass it along to make sure everybody has a handout by the time I get to it. All right, so the question is, you know, what's a derivative, okay, and why do engineers need to know it? And like all questions that we ask in here, we try and answer them by example, okay? So this begins the derivative, okay, and the example we're going to look at is velocity and acceleration in free fall. Okay, and in fact, the derivative lab that you'll be doing in lab is looking at this exact problem. Okay, and so, for example, let's take a look at a ball which is dropped in the vertical plane, okay, from a certain height, okay, we'll say from a height y equals 1.0 meters. Okay, and so what I mean here is I've got the ball. It's held above the ground, so it has initially 0 velocity. So this is time t equals 0 right here. Okay, and what I'm going to do is measure the height of this ball, right, from the ground. So right here is the coordinate y as a function of time, y of t. Okay, and so up here at t equals 0, this is y equals 1.0. Okay, and the units are meters. And so this thing's going to fall down. Okay, and at some later point in time, it's going to hit the ground. Okay, and so down here, you know, the question is, what is the time? Okay, and of course, at this level, the y value is 0. Okay, so let's see if we can do an experiment here to figure this out. Okay, I didn't bring a ball with me today, but I got a marker that's close enough. Anybody have a watch that's got, say, like a couple of digits on the stopwatch?
That's me.
That's you. Okay, so I got a volunteer over here. You gotta take a couple measurements. Now you gotta be good because we're gonna try and do 1 meter. And this is a little ballpark, right? I'm gonna say that roughly my hip is about a meter here. I'm not quite a 6 foot tall guy, but this is pretty close.
Well, I need to figure out how to get this thing to work.
All right. Anybody else? We can do more than one at once to get some corroboration here. We got another one there, cell phone one. All right, so here's how we're going to do this. I'm going to do a 3, 2, 1, okay? And on 1, like when I say 1, I'm going to let go, right? And when it hits the ground, I need the measurement. So when I say 1, it's button. When it hits the ground, it's button again. Okay, so this is probably going to happen in less than a second, right? So get the thumb limber. Okay, are you ready? 3, 2, 1. What do we got?
It's like 0.35 seconds.
3.5.
I got 3.5.
3.5.
I got 0.383.
3.8. 0.440. 40. 3.9. Okay, let's try one more.
All these things are random, so
This is pretty close. So we're getting in the neighborhood of 0.35, 0.4 or something. Okay, let's try this again. Are you ready?
wait.
Everybody get reset?
Yeah.
All right. 3, 2, 1.
Oh,
What do you got? Point what? 3.9 again?
Yeah, I got
mine was way too off. It like
Yours was?
0.47.
0.47.
Which one do we choose?
3, 4.
All those are going to be different.
All right. So I did this measurement myself with more advanced technology. Okay? And the number I got was in the ballpark of what you just said, 0.452. Okay? 0.452, so maybe a little bit longer than what you guys had there. Okay? And that is the seconds. Okay? And so what I'd like to think about is, you know, from an engineering standpoint, there's a lot of things to think about. This is an impact kind of problem, right? And so if I'm designing like a vehicle, right, that I want to make sure is safe for the passengers, then I want to think about how the energy is dissipated at the impact, right? And so it's a speed and an impact kind of problem. And so the kind of things I'm interested in are, you know, am I going to break this, right? If this thing is my parents' expensive antique glass globe, I might be concerned about if it breaks. If it's a racquetball, then maybe I'm bouncing it on purpose. Maybe I'm not even letting it free fall, but I'm giving it an initial velocity down, right? And so there's lots of different things that an engineer might design here. But no matter what, any of those questions, okay, I probably want to have some idea of how fast this thing's going when it hits the ground, right? And, you know, take a look at the data points that I have here. Can I say anything about the speed of this ball based on the data that's on the board right now? It's negative acceleration. Okay. So let me go back to try and be very exact with my language. Can I say anything about the speed of this ball? All right. The speed is changing. Can I tell that from the data points that are up on the board? No? Yes?
You do y2 minus y1 over
So now it's going to get you the average velocity.
All right, so I can compute a speed, right? It's like in 6th grade is the first time they start trying to int some algebra in. It's distance equals what? Rate times time, right? It's like the first equation they introduced. Distance equals rate times time. Okay, and so rate then, as a result, would be equal to what? Distance divided by time would be rate, right? And so like miles per hour, right? Meters per second, distance divided by time. So I do have some position values here, right? Some locations, and I do have some time. So I can compute a measure of speed. And that would tell me what? Is that the speed that it starts with? Right. It's not the speed where it starts. It's not the speed where it finishes, but it's at least, you know, an average value. Great. So let's look at that. Number one, let's look at the average AVG velocity. Okay. And just to be clear, in this kind of discussion, I'm throwing around the word velocity and speed the same way. We know that velocity is a vector quantity. It has magnitude and direction. This is a one-dimensional problem, straight up and down. Okay, so by velocity, I mean the speed here, the magnitude of the velocity. Okay, and so average velocity. So who wants to give me a definition of the average velocity? I'm going to call it V bar. We like to use a bar for an average value.
V initial minus V final over 2.
V initial minus V final divided by 2.
V initial plus V final.
Okay, so just to be clear here, do I have the final velocity up on the board?
No.
So I could average anything by taking two numbers, adding them, and dividing by 2. So if I knew the velocity at both points, then I could propose that. But with the data given here, back to the whole distance equals rate times time, how would I compute the average velocity? You want another crack?
Total distance traveled divided by total elapsed time.
OK, total distance divided by total time. So what I have on the board is values of the position y, and I have values of the time. So how could I write this in terms of y and t? Delta values, right? Delta meaning change. So this is delta y divided by delta t, where the triangle there, delta, that means the change. Okay? In problems that depend on time, we usually use final minus initial, right, when we think about change. Okay? As long as you're consistent, you're doing a delta in the numerator and denominator. So this is back like slopes of lines, right? I could use either way. But with time, we like to think about this as final minus initial. Okay? And so you could think about this as y2 minus y1, right, divided by t2 minus t1. And so let's go ahead and compute this thing. So what's my average velocity here? What's the final y value? y2. Hey, I'm using 1s and 2s, right? But the idea is 2 is the final and 1 is the initial. It's 2 points in time. So the final value here is at 0, right? So y2 is the 0 minus what's the initial position? 1 meter. So it's 1.0 divided by the change in time. T2 is the time where I'm at the ground. 0.452 minus what's the initial time? 0. Okay, so somebody crank that out on a calculator for me. What do we get? Minus 2.21. Does this thing have units on it? Meters per second. Okay, so I've got an average velocity minus 2.21 meters per second. Great. So let me ask you this question. Let's say I'm a materials engineer, okay, and I want to design this thing out of just the right kind of glass that's not going to break at a certain speed, okay? If I know that the average velocity is minus 2.21, can I select the glass based on that? What's the problem there? It's not the highest. That's a good way to put it. It's not the highest velocity. The other response was it's not the impact velocity. Okay, so apart from your basic intuition, how do you know mathematically that the impact velocity is higher than the average velocity? Okay, so he said because it has acceleration, but that's physics knowledge, right? I'm just talking about these numbers on the board. Yes?
Wouldn't your distance be smaller and your time be greater the closer you get to the ground? So you can do it that way.
Your distance smaller and time greater.
But as it gets closer, it's going to be smaller when the time's going to get closer to the ground.
So, okay, I guess I'm not getting the rationale. I mean, why is it that the impact speed has to be greater than the average?
You change the values, like so you go like 0.5 meters, but then you have to know what time it would be at, like what the time would be at and compute that value.
Yep. But just based on these two data points, okay? And so without your knowledge of physics of what's happening here, right? We've had several people repeatedly say, hey, it's accelerating. So we know what that means if we've had physics, and so it's driving the answer. I want a mathematical answer. Okay, give me a math reason why, the impact has to be higher than the average.
The average is the sum of the highest and the lowest values over a period, so it's like
And what's the lowest value?
0.
0. Okay, that's the reason why, because it starts at rest. Okay, that's the reason why the impact has to be bigger than the average. Okay, whatever kind of function this is, okay, if you know what the physics is, maybe you know the answer. Is the position linear with time? Is it quadratic with time? Is it cubic? Is it a sinusoid? I don't know. If I know some physics, maybe I've got the answer. Okay, but no matter what the behavior is, if it starts at 0, right, and I've got the average over here, okay, then it's going to have to be bigger than the average. Okay, so if it's bigger than the average, then in engineering design in general, averages don't govern design. Worst case scenarios govern design. Okay, so failure of materials, weakest link, inclusion in the microstructure, that governs the failure. Okay, and so average is great, okay, but I can't design based on the average. All right, so what I really want to know is I want to know the speed at impact. Okay, and so this is the question. Do I have enough data right here to determine the speed at impact? No? Yes? I do? Okay, so how would I compute, based on this data, how would I compute the speed at impact? Say what? Initial velocity is how much? 0. Okay, so if I've had some physics and I know some governing equations, I might be able to figure this out. But we're trying to be like Isaac Newton here. Okay, I don't have the laws of motion yet. Okay, I'm just taking some data.
Does that mean we can fudge your numbers too?
Can fudge the numbers. I don't like the word fudge, okay, but we can have numbers that are approximate, okay, and get an idea. So that begs the question. I like the line of questioning before about can we get closer to the ground over here, right? So what if we took some more data, right? Like in the lab you guys are doing on this, okay, we'll be doing on this. You're going to take data at lots of points in time, okay, on the way down. Okay, and so to get the speed at impact, you need more data. Okay, so for example, let's say that we had really fast thumbs, okay, and we could do this thing in time. We've got these ultrasonic displacement centers in the lab, okay, that can actually do this for you. So you'll take some data like this, okay, and what I'm going to do is put some example results, okay, of more data. So we'll make a little table here. We'll put the time, okay, over here in seconds, and we'll put the position y of t in meters, and we'll make a little table at various points in time. Okay, and so what we'll do is we'll just step along here. We know that it takes a little less than half a second. Okay, and so we'll go about every 0.1 until we hit the end. So we'll start at 0. At t equals 0, we've got a y of 1.0. Okay, and then at 0.1, we've got a y of 0.951. Okay, again, this is separately recorded data. At 0.2, we've got a y of 0.804. Okay, at 0.3, we've got a y of 0.559. Okay, at 0.4, we've got a y of 0.215. Okay, and at the endpoint, 0.452, I've got y equals 0. Okay, so here's my table, okay, with y values at certain points in time. Okay, so here's something that's kind of interesting. Let's just look at the raw numbers for a minute to think about the physics. In the first tenth of a second, okay, the position changes by what percentage of the total height? About 5%. So I go about 5% of the way in the first tenth of a second. Okay? In the last half of a tenth of a second, I go how much of the way? 21% of the way. Is this thing moving at a constant speed? No. Okay, so the intuition about, hey, the speed is changing, got to get a different speed down here than the average. Well, the numbers looks like that'll be the case. Okay, so if I want to get an estimate of the speed at impact, based on this data, could I get a better estimate than I got based on just these two data points? All right, so what if I take a look at each one of these intervals, okay, and I calculate an average speed in every one of the intervals? Right? And again, clearly, in the first interval, I only went 5% of the way in a tenth of a second. In the last interval, this one's less than a tenth, right? It says half the interval, and I went 21% of the way. So I'm going to get a different answer for that speed. Okay, so what are the average speeds in each interval? Okay, and so for example, let me do one example calculation. Okay, let's use the first interval. So what I mean by that is a span of time between 0 and 0.1. Okay, so for example, for t, this interval, 0 to 0.1, I'm using brackets for the interval like they would in a math book, right? From 0 to 0.1, starting point, end point, including those points. Okay, what is the average velocity? Okay, in this case, I'm going to get a v bar, which is final minus initial, right, for each one. So yeah, help me out. First interval from 0 to 0.1, the final value, right? So it's going to be change in y divided by change in time. What's the final y value? It's this guy, right? Okay, y value is on the bottom, so it's the 0.951. So 0.951 minus 1.0, the initial y value, okay, divided by the change in time, which is how much? It's 0.1, but it's the final 0.1 minus the initial 0.0. Somebody run that on a calculator for me. Minus 0.490. This is also meters per second. Okay, so interestingly, right, the average velocity overall, minus 2.21, very close to the top when I only went 5% of the way. The average velocity in that first little interval is only 0.49. So it starts out moving a lot slower. Right? Again, the idea that by the end, it better be moving a lot faster to make up the average. You guys with me here?
I am.
Very good. So what would this look like for every interval? We just did the first calculation. I'm going to write up the answers. Yes?
We're thinking about this in a physical sense, like, because 0.49 is actually greater than negative 0.49 is actually greater than negative 2.2 number. We're thinking about it.
Yeah. So this is a good point. So he's talking about algebraically in terms of positive and negative. Okay, in terms of positive and negative numbers, this is a greater number. Okay, and that's true. So this is great. I should have pointed this out. Why is it that I have a negative here at all? It's going down, but keep in mind, what's stopping me from doing this entire problem where I do this instead? Nothing's stopping me. It's arbitrary. Okay, so I choose the coordinate system. I say y equals 0 at the ground. Once I set up that framework, I interpret what the numbers mean. I could flip this whole problem upside down, say y equals 0 at the top, right? And then the speeds I got would all be positive numbers. But in the end, the question is, what's the average? What's the speed at impact? I actually don't care about the sign, SIGN, right? I just care about the number, 2.21. So that's a great point. The negative here just denotes the fact that it's going down because I chose positive as pointing up. That's it. OK, so the idea that it is greater or less than the magnitude of this speed is less than. It is slower than the magnitude of this speed. Good point. Questions on that? All right, very good. So, what would this look like for the entire set of intervals? Okay, and so we'll just go ahead and compute this for each interval. Right, we'll put the answer here. We'll put the v bar value in meters per second. Okay, and so I'll go ahead and write up the exact intervals that correspond to these numbers right here. So we just calculated this one, the 0.1 interval, and we got minus 0.490. The next interval was between 0.1 and 0.2, okay, and that's the difference between these two numbers here. Okay, and if you compute that, you get minus 1.47. If you look at the next one, 0.2 and 0.3, okay, then you're talking about the difference between these two numbers, the 0.559 and the 804. You get minus 2.45. Okay, so halfway down, well, I've kind of passed up, right, the average velocity, okay, over here. Okay, and then between 0.3 and 0.4, okay, if you compute it, you get minus 3.44. Right? So now I'm past the midspan. I'm going faster than the average, minus 3.44. And then the very last interval, keep in mind, the time change is different. It's 0.4 to 0.452. Okay? And so I have to do that accordingly, right? The time change here is 0.052. It's not 0.1. Okay? But when I do it, I get this, minus 4.13. So based on this data, if I was forced right now to give my best possible approximation to the speed at impact, because I'm the materials engineer and I got to select the piece of glass I'm going to use to make this out of, okay, what number would I choose? Yeah, I'd have to choose the best I've got, right, with the best possible answer. Okay, so the speed at impact, okay, v is approximately, right, best we got here, minus 4.13, right, the magnitude, 4.13 meters per second. Okay, and so here's the thing. If I'm now the boss, and I'm like, well, are you sure about that? Should we choose this material right here? Okay, and I really want to be sure this thing doesn't break. Is the real speed greater or less than that 4.13? Yeah, so this is a problem in engineering design. When you pick an approximate answer and you know ahead of time that it's non-conservative, right? The right answer is a more worst case than the answer you're going with. Not good, right? When in doubt in engineering design, it's the other way around. Let's be conservative, let's overestimate, right? Let's not underestimate. So we got an issue because we're underestimating over here. Yes?
I know one rule in design and stuff for engineering is that there's always the 0.02 plus minus for 002. Basically, like, it's never completely accurate at the exact same time.
So you're acknowledging that in general in engineering, trying to get things better than like 5% in an experimental result depends what you're measuring. We have, this is an aside, okay, but I used to work in mechanical behavior, life prediction at the Air Force, right? And they're trying to figure out when to throw away engine parts because they might have fatigue cracks, right? And the problem with that is the engine part, like a disc, is $250,000, one disc, and the engine's got a whole line of discs in it, right? And the Air Force says if there's a probability 1 in 1,000 that this thing's got a crack and is going to fail, I got to go retire it and put it in the barn somewhere. And then the research engineers, the irony engineers, they go to the barn and they say, let's figure out how long this really could have lasted. Okay? And then they put it in a thing and they spin it forever and they keep spinning it and putting loads on it and it just doesn't break. And they got a $250,000 part that could have been used twice as long. Okay? And right. So the methods we use to life those kind of parts, right, are based on fatigue crack growth data. In the world of fatigue crack growth data, if you can get the growth of cracks repeated to within 100% error, that's pretty good. This is also why we throw out $250,000 discs. Okay? So, and as a mechanical engineer, I still get window seats from time to time. I do a lot of flying. Okay? And so I'm looking for the cracks. Okay? But the point is, it depends, right? So sometimes 100% is as good as we're going to get. Sometimes it's very, very accurate. I mean, there's certain properties of materials and things you can measure it down in a repeated way, to way better than 1% repeatability all the time. Okay? So it depends. Depends on your discipline, et cetera. Okay? But in this problem, if I want the speed at impact, okay, what I really want to know is how many more data points should I get here, right? Okay, so if I want the exact answer, how many data points do I need? I need infinity, okay? The exact answer, okay, this requires, okay, infinite data. Okay, that's the point. I got to have infinity. Now, in practice, if I said I want the answer to 3 significant digits, as the intervals get closer and closer to the end, there's going to be some point where the 3rd digit's not changing. Okay, so you got to realize from an engineering standpoint, there is no infinity. I can get as close as I want to things. I can write an algorithm in MATLAB to stop when the difference is now in the 4th digit, right? Because as far as I'm concerned, that's the answer, 3 digits. Okay, so there's the practical right answer, and then there's the real exact answer to 1,000 digits. What's the exact answer? Okay, and the only way I'm going to get there is if I get so close to this 0.452 that I can carry 1,000 digits out and it's the same answer. Okay, and so I need an infinite number of data points. So the question is there a way to represent that mathematically without actually needing an infinite number of points over here? Right, that's the question. So what this really means, I'm going to write some stuff down that if you've had calculus might look familiar. If you've had no calculus, you're going to say, what the heck did he just write down? Okay, and so let me explain this to you. What we really want to say is what I want here is the velocity v. I want it evaluated, right, at impact at 0.452. So this is not multiplied by, this is v of t, evaluated at 0.452. The right answer here is what we call a limit, L-I-M, right, as t approaches that point, 0.452. Okay? And what I'm going to do is, as close to this point as I want to get, any value of t, y of t, as close to 0.452, I'm going to compute the average, just like I did there. Right? So what this is the y value evaluated at 0.452 minus the y value at whatever time I'm talking about as t gets as close as I want, 0.451999999, as many nines as I want. Okay? Right here, take the difference and now subtract the numbers. The final is 0.452, right? The initial is whatever time I'm at, 0.451999999. Okay? So it's what we call a limiting process, as close as I can get to that point. Okay? And so here's the thing. This is the interpretation of infinite data, okay, for this exact number, for 0.452. But what I'd like to think about is really at any time, okay, at any value of time, okay, I can get the speed instantaneously. Okay, so we'll say the instantaneous velocity, okay, by the same argument here is the following. It is v at any value of time, the instantaneous speed, what we call a limit, LIM, as the time interval gets really small, delta t approaches 0, okay, of change in y divided by change in time. So it's a statement that it's an average speed, change in y over change in time, over as small a time interval as I want. This delta t can get as close to 0 as I like. That's what I'm doing when I say, give me more data points, get as close to 0.452 as I want. Okay, but now instead of just saying it's the impact speed at 0.452, I could say anywhere, right? Right here, at t equals 0. Whatever, 21456. What's the speed right there? Well, I could do this. Take a delta y over delta t right there, as close as I can get to that change in time at that point, and get the answer. Okay, the way you can write this out is the y value really at any time t, right? So it is the limit as delta t approaches 0. Okay, we'll take the final y evaluated at any time plus a small time change, t plus delta t, and then we will subtract the starting point y of t, and we will divide by delta t. Okay. So if you've had calculus before, you might recognize either one, okay, of these notations to be, by definition, the triple equal sign. That means is equal by definition to what we call the derivative, dy dt. Okay, so this notation, dy dt, looks like division. It looks like dy divided by dt. The d symbol really means the delta. So understand what you're doing. You're taking a change in this variable divided by a change in this variable, but you're only looking at a change over an infinitesimal amount of time. Okay? And so this dy dt, okay, is dy dt is the derivative, okay, of y of t, okay, and the language is with respect to t, with respect to time. Okay? So you can have y that is a function of x. You can have voltage that's a function of current. Any variable that's a function of another variable, I can apply the idea of a derivative, right? An instantaneous rate of change. When we live in the world of position and time, an instantaneous change is a statement of velocity at a point. When I live in a world of current and voltage, it might mean something else. Okay? When I think of a deflection of a beam, it might mean something else. Okay, but what is always the same is the idea that I'm looking at a change in one variable over a very small interval of the other variable. This is the definition of the derivative. Questions about that before I move forward? Okay, and so one of the things about this class that I want to be clear, students that have not had calculus, we are trying to play forward for you the big picture of what you're going to see again in calculus, and to really hone in on the way we really use this idea in our classes. For those of you that have already had calculus, what we're hoping is to revisit this and get a little bit of aha going on for students that could work all kinds of derivatives left and right like they were doing a Sudoku puzzle, okay, but have absolutely no idea why that actually matters. Okay, and so if that's you, that's where we're trying to go. Okay, so anybody of your background, questions about this basic definition before we move forward? All right, so I passed out this sheet. Okay, and the way we use derivatives in engineering is very much related to the graphics on the sheet. So I'm going to pull this thing back up and talk about this briefly. Okay, and then we're going to use this idea of derivatives to answer this question, the speed at impact here.
Is the second derivative the acceleration?
It is. We're going to get to that. Okay.
So it's a jerk.
Yeah.
I thought velocity.
Is this using MATLAB?
Nope. I'm just going to pull the sheet up because it's posted.
This sheet?
The sheet that I passed out. So you guys have a derivative handout. Okay, and I just want to talk about this briefly here.
Didn't notice the back. Why don't I ever remember using sine hx?
Okay, so here we go. Here's what you guys have in the sheet. This is the colored version. Okay, and so we've got the definition of the derivative, dy dt of a function y of t. Okay, here's the mathematical interpretation in a graphical sense. Okay, so we just talked about it in the context of speed. Change in position over change in very small time gives me a speed right at a point. Instantaneous velocity. Okay, but now, what if I plot y of t, that's the blue line here, as a function of time? Incidentally, what kind of function do you think this blue line is here? Yeah, it looks like a parabola. Okay, so that's a quadratic that we happen to have drawn there. Okay, so let's think about this. If I take any 2 points on the curve, any 2 points on the blue curve, each point has a y value and a time value, here and here. Time, independent variable, y, dependent variable. Let's think about the stuff we just did. Average velocity, change in y, divided by change in time. Well, take a look at the graph. If these are the 2 points I choose, isn't the change in y just the opposite side of the triangle here? And isn't the change in time the adjacent side here? So if I take any 2 points and connect them with a line, then delta y over delta t is what for that line? So physically, with position and time, it's velocity. That's true. I heard the word average. That's true. The exam you just took, when you took rise over run, you were computing what? Slope. So from a graphical standpoint here, if I take any 2 points on any curve, and I take change in y over change in time, that gives me the slope of the line that connects the 2 points. That line is what we call a secant line. Any 2 points on a curve, connected 2 points, the slope of the line is the average. Now, if I want to think about the slope of the line now as being a velocity, then a high velocity would have what? Steep slope or a not steep slope? Steep. What would a position of rest, a velocity of rest be? That would be horizontal, right, when a slope is 0. So I mean, look where even these points are. Clearly, at the first point, I got a slope like this. That's one velocity. Over here, I got a slope the other way. That looks negative, going backwards. There's a place in the middle where I've got no slope at all. So clearly, this average value, not that helpful for me in the design. Right? In fact, if I pick points that are exactly symmetric across this thing, what's the average value? 0, right? I'm not moving. If I grab this point and this point right here, the line that connects them is horizontal. Okay, so what I really want to know is, hey, at any point in time, how fast am I going? I need the speed right here. So at this time, say 0.2, if I want to know the speed, what do I need to do with the secant line? I need to take the second point, and I need to back it down the curve, right? And think about what happens to this line. As I back the point down the curve, the secant line becomes ultimately the tangent line. Okay? And a tangent line means a line that just kisses a curve at one point. Okay? And so that's what the tangent line is. So backing this point down the curve is doing what to delta t? Making it smaller and smaller and smaller. Right? As I back this point down, the delta t distance is getting smaller and smaller and smaller. So literally this limit, as delta t goes to 0, graphically it means taking a secant line and turning it into a tangent line. So why in the world does an engineer care about that? Key point here. When we design, we don't want averages. We want weakest links. We want to manage the power generated. I don't care about the average power. I care about the peak power. Okay? I don't care about the max, the average value of the stress in the bar. Right? I need to know the maximum stress in the bar. So if I've got a tool now that can tell me at any point, instantaneously, what's the slope? Then if I want to find the design value, I'm looking for places that have no slope, right? Like the maximum height, for example, it's a flat spot, right? Like the minimum power, if the curve went upside down, it's the flat spot. Okay, so engineers need concepts of derivatives in a very fundamental way. Number one, because we need to find the flat spots. All right, the flat spots are the design parameters that we use. Okay, so right away I know that if I could compute a derivative, I could find the places where this thing's flat. And I can now use this in design. So what I'd like to do is jump forward to some derivatives we can use. Now if you've had calculus, you already know how to take a whole bunch of derivatives. Okay, and that's great. If you haven't, I need you to know how to take these derivatives. Okay, because these derivatives are the ones that pop up in the first 2 years of engineering all over the place. Okay, so for example, if I have a function sine of omega t, like we just talked about in sinusoids, right? Week and a half ago. Omega is the frequency, time is the independent variable, right? So omega is a constant value here, right? T is the variable. Then the derivative dy dt, turns out derivative of the sine is a cosine, but the omega comes out front. If I have cosine omega t, the derivative of the cosine function is the sine function with a negative, and an omega comes out front. If I have an exponential function, haven't seen much of these in the class yet, we'll see a lot of them moving forward, e to the st, s is any number, any parameter, e to the 3t, e to the 4t, e to the pi t, whatever. The derivative is still e to the st, except now the s comes out. Okay? If I have t to a power, t to the n, the derivative is now the power n times 1 less power. So if I have a function that's, say, quadratic, t squared, the derivative of quadratic now would be 2 times t. When I take derivatives of polynomials, it knocks it down by 1 order, okay, every time I do a derivative. Here's some general rules that are useful. If I take a constant times a function and I take its derivative, the constant just sits there and the derivative goes. Okay? Somebody that's had calculus before, can you explain to me why, when there's a constant out in front and I take the derivative, that the constant stays out front in the answer? Go ahead.
Well, the constant would just shift the graph either in the y or the x direction.
Wait, so be clear. Which direction does the constant shift the graph? C times y of t. So if I plot on the same graph, 2 times y of t. So this is y of t, and now I plot 2y of t. What's the difference in the graph? Does it shift? What was that? It stretches it. Doesn't shift. It stretches. Does it change the t values? So every t value is the same, and every y value is twice as tall, right? So think about the process. Change in y over change in time. If every y value is twice as tall, and all the t's are the same, then the net answer, when I divide the change in y by the change in time, it's a factor of 2. Right? There's a 2 in every y value. There's no 2 in the t values. It stretches it out. Graphically, stretching it out doubles the slope. Right? At every point, it doubles the slope. At the point where it's 0, it still doubles the slope. 2 times 0 is still 0. Right? Okay, so a lot of these rules you take for granted in calculus. Students that have had calculus, I really want you to take some of the whys away when we review calculus here, because the whys is what stops you from having to memorize things and has you be able to really just understand things. Okay, and that's where you need to be. A successful engineer doesn't remember anything. Okay? That's it. If you're a successful engineer, you don't remember anything. You don't need to remember anything. You could figure anything out. Okay, and that's the ultimate role of an engineer. The stuff you happen to remember is just because you used it so much, it's just right there. Okay, but you're not trying to remember, you understand. All right, so over here, y1 plus y2. If I add the functions, well, when I take the derivative of the sum, so now I have a polynomial. T cubed plus t squared plus t to the first with constants in front. If I take the derivative, I can do it term by term. 1 term at a time, take the derivative. Who wants to give me a y on that? Somebody that took calculus. Why is it, if I have multiple terms added up, when I take the derivative, I can just add the terms? It's a little hard to view it graphically, but can we think about it from an algebra standpoint? All right, so if I have two functions, y1 and y2, one of them's this, another one doesn't have to be quadratic, it could be anything. When I add y1 and y2, it means at every time value, I take both of those y's and I add them up, right? When I do a derivative, at every point, I'm taking the difference in the two y's, I'm dividing by the difference in the times. So if each one of these y's is now two terms, y1 plus y2, when I divide, can I distribute to both terms? The answer is just algebra, right? It's because division is distributive over addition, right? I mean, it's just the way it works. I can add two numbers up here. Well, that's the same as dividing both of those numbers by delta t. And I can just rearrange the algebra to show that that is the way it works. Okay, so these are useful rules in derivatives because now I can start combining these. I could have like an e to the st plus a sine omega t plus a t cubed, and I can line them all up, and what's right here, I can use these rules to take the derivative. So if you've never had calculus, the derivatives on this front side of this page are the ones we need you to be able to do. Okay, there's one other thing called the product rule that we'll use a little bit later in some examples, and you'll learn that as well. You can find that on the back side, where we have, shamelessly pirated, the inside cover to your calculus book, okay, that you'll be buying. And so look, this is what the people that write the calculus book view as common rules of derivatives that calculus students need to be able to do. We're not going to do every type of complicated derivative in here. We're going to do the big picture stuff, and we're going to solve problems. Okay, but you know, bottom line is some of the more general ones, some of the basic ones we already have, the trig functions, the exponentials, you can see them on the back here. Okay, and then the more general rules, things like product rule, chain rule, if you've had calculus, you've learned that before. All of that's on the back. Okay, in this class, these are the kind of derivatives you'll be asked to do by hand. We know that you've got TI-89s, you've got MATLAB, you've got everything else if you need to do a complicated derivative. And we know that you're all going to take calculus, where you'll spend a lot of time working complicated derivatives by hand. Okay? If you can do all these derivatives, 90% of all problems in an engineering book in the first 2 years are these. You know, it's polynomial, it's sinusoidal, it's an exponential, whatever. Okay, so these are the tools we kind of need to move forward. Questions on that? All right. So, moving on. Can we now use this tool, derivatives, to answer some of the physics here?
I have a question.
Yeah, question.
Very simple one. My dad's told me he's been using MATLAB ever since more than 20 years ago.
Yep.
How long has that program been around?
It's been around a while. There's a guy that teaches here. Ron Taylor is a NT faculty member in computer science. Okay, also a really accomplished researcher for University of Dayton Research Institute before that. And you know, so he loves to teach, and he's been teaching for us for a number of years. When I was an undergraduate student, I took a numerical methods class taught by that guy, and he walked out with a floppy 3.5 drive with MATLAB on it. And he was like, this is the next big thing, guys. Everybody install this onto your PC. And half the class is like, well, I don't own a PC yet, you know, and so whatever. So you could take it to the public lab. So that was in 1992.
That's the same year my dad.
So there you go. So MATLAB, early 1990s, probably late 80s it was developed, commercialized early, you know, after that. But it's, yeah, I mean, MATLAB, it is the way engineers compute things. Every engineering program in the country, they've got MATLAB in their curriculum. So.
And it's the most important alternative to a calculator.
Yeah, I mean, it is a programming tool. It's a tool for visualizing data. It's just very powerful, right? So you'll appreciate the MATLAB if you don't appreciate it yet, okay? All right, so moving on. So can we use this idea of the derivative? So here's what I'm going to do. We've got all this data, okay? And now we've got a derivative. Let's go back to this problem, and let's see if we can put an equation on the data, and then use this calculus idea, derivatives, to compute the answer. All right, so here's the idea. Okay, so this is back to the problem. So let's say that we do a quadratic curve fit because we have some sense that this free fall is starting slowly, right, and then speeding up, but not, the position is changing in time faster than linearly, right? We looked at the intervals. That very last interval is a lot faster than the one at the beginning, so it's not going to be a line, so maybe it's quadratic. Okay, so let's say we do a quadratic curve fit, right, in MATLAB or in Excel or wherever else of the data. Okay, and I'm going to give you the answer to that curve fit. Okay, here's what I get. Y of t is the starting value 1.0 minus 4.905 times t squared. Okay. And let's just go now back to the question. Okay. What's the speed at impact? So, given now that we know we got this tool called a derivative, right? And we know that when I have position and time, that derivative gives me velocity, instantaneous velocity. If I want the speed at impact, given this position, what should be my strategy now? Find a derivative of the equation. Does that give me the speed right at impact? All right, so the derivative of the equation will give me the velocity at any time t. And if I want the speed at impact, I plug in what value at t? Yeah, I plug in the 0.452. Okay, incidentally, what we just did here is have a plan. Okay, in engineering, always a good idea. Before you do a piece of math, have a plan. Know where you're going with it, right? So what's the plan? Let's calculate the derivative. At any time t, the velocity v of t, okay, let me stick with the same looking v's that I had. V of t, okay, is equal to, by definition, dy dt. Okay? And so let's take the derivative. This is the derivative with respect to time. Here's a way I'll write this. d dt, like an operator. Take the derivative of this equation, 1.0 minus 4.905 t squared. Okay, so this notation that I wrote here, d dt of that, is just the way we write take the derivative of this expression. Okay? So I would argue that what is on the front side of this sheet, okay, if you've never had calculus in your life, I'm not asking you to remember how to do this. I'm asking you to explain to me how to do this based on what's on the sheet. Is there anybody that has not had calculus that wants to kind of help walk me through how do I take this derivative? Looking for a volunteer here. Not mandatory. Anybody never had calculus want to give this a crack? Okay, because otherwise I'm going to go after somebody that has had calculus to help us. You want to give it a go? All right, so you're skipping a few steps. Okay, you're getting there. Walk me through this. I got how many terms here? I got 2 terms. So can we apply the rule that says if I have 2 terms, I can do derivatives one at a time? Let's start with that. Okay, incidentally, we will very rapidly reach the point that when we know how to take derivatives quickly, I'll do in one line as much as I can do. Okay, at this point, I want to make it clear what we're doing. Okay, so to take this derivative, right, is this not then the same is the derivative of each of these terms? So it's the derivative d dt of 1.0. I got to do that one. And then a minus is the same as a plus with a negative, right? So it's really plus the derivative d dt of minus 4.905 t squared. All right, so I broke this thing into 2 terms because I'm allowed to do that, right? So we keep running with this. You seem to ignore this part. All right, so you're right. The derivative of this equals 0. Can you explain to me why? There's no t value with it, so why does that mean the derivative is 0? OK? That's fine. All the way in the back? You got an explanation?
Basically, 1 is times t to 0.
OK.
0 comes down.
All right, I like that argument. So he's saying, look, isn't 1 just t to the 0? And don't I have a t to a power law that says t to the 0 is 0 times t to the negative 1? Right? So the formula captures it. So one answer for y is because the formula said so. Now, based on what you know about me, do I like that answer? No. Maybe. OK, it's good. The formula says so. Can somebody give me another reason?
It's a constant.
OK.
So if you're measuring how it changes, it doesn't change.
Oh, I love this answer. Right? It's forget the math. It's a constant. The rate of change is 0. I like that answer. OK, give me a third. What if I'm the calculus prof and I want to think about this from an analytical geometry, right? Like I want to graph this thing. Somebody give me a graphical explanation for this? It's a straight line. So is the derivative of all straight lines 0? OK, what kind of straight line is this? It's a horizontal line, right? This term, just to be clear, is the function y of t. This is t. This is it. Right? This number is 1.0.
Yes.
What's the slope of this line?
0.
0. That's the reason I'm looking for. Okay? The slope of the line is 0. I love the physical reason. It's not changing. Derivative is a rate of change. Okay? So either one of those, absolutely. And if it helps you to remember it, the formula said so. That's cool too. Okay? All right, great. So this term's gone because constants don't change 0. Okay? How about the next term?
Are we going to apply the famous shortcut for this one?
What's the famous shortcut?
Well, the negative 4.905 is a constant. That's starting out, right?
So what do I do with that constant? Keep going with this.
Put it on the outside.
OK, so I got 0 in the first term. I'm over to here. The constant stays out front.
Yes.
It's right on the sheet. We talked about it. Stretches the function. So great. Put it out front. So it's minus 4.905. Now I still need the derivative of this function, t squared, right?
Yes.
So is t squared one of the functions on the sheet? It's t to the n power, right? The n is what? 2. So I got a formula for that. OK, incidentally, if you want the y's behind this formula, I got to save something for the math department. Okay, the math department will derive these formulas. You can get them straight from the definition of the derivative. Okay? If you really want to see it before math, come to office hours. Okay, we can do that for you. All right, but the point is I got a formula, and the t squared, t to the n, it's n times t to the n minus 1. So n minus 1 is how much? 1. So this is minus 4.905. The derivative of this, the 2 comes down, times t to the first power, right? So it's just 2t. So what he did in one immediate answer was he looked at this and he said the answer is 2 times that times t. Okay, and that is fine, right? When we get to the exam on this, anything that can be reasonably done in your head in one line is fine. You don't have to show all this in between. This is just me making it clear how we're getting there. Okay, so v of t then apparently is, what's 2 times minus 4.905? Minus 9.81, interesting, t. Okay, does this have units on it?
Wait a minute. I know that formula.
Meters per second. What's 9.81, guys? All right, so was my question, what's the velocity at any time?
No acceleration. Take another.
What was my question? The question was the speed at impact, right? So at impact, what do I do with this answer for the velocity at any time t? At impact, I need to sub t is equal to 0.452. Let's plug it in. V is equal to minus 9.81 times 0.452. Somebody give me a number. Right? I'm plugging in the endpoint here, right, and evaluating the speed, v, at that time. Give me a number. Minus 4.43. Does that have units on it? Meter per second. Okay, and so, you know, this is the speed at impact. Okay, now, the last interval. About how close was I? Three-tenths, right, out of 4. So a little less than 10% error, 7.5% error, okay? And so, you know, I got pretty close, but I wasn't there. All right, we'll pick up here next time, guys.